Okay, I think it's 1 o'clock. Can you hear me? Is it okay? Am I understandable?
I can hear you.
Great. Okay, at the moment we are here. Maria, you also can hear?
Can hear you.
Yeah, great. Okay, it's a little bit a pity that we at the moment are only 4 persons. Hopefully we get some more over the time. About the structure, I think you all have read. We have the presentations. You prepared your presentation in 5 minutes as a you have recorded it. Afterwards, we have around about 5 minutes time for discuss the topics. Please write your topics in the chat, and I try to moderate the questions. Hopefully, we have a lot of questions, but I think it's a really interesting session because we have a very interesting topic, and we have several aspects discussed in this specific field of knowledge-based engineering. But in summary, my feeling is there are a lot of homogeneous topics, and it gives a lot of aspects where we found dependencies and where we have points for discussions. Okay, let's start with the first presentation. This first presentation is from Mr. Harald Anacker. He's from the Fraunhofer Institute for Mechatronic Design, Systems Design in Paderborn in Germany. He is the head of the department Systems Engineering there. He made his PhD in 2015, and now he is head of the department. So unfortunately, it seems that Mr. Anacker is not here, but nevertheless, let's hear the presentation, and maybe this questions are difficult, but maybe we found discussion points. Please, can you start, Ivan?
Okay, I will start now.
Okay, we can't hear at the moment.
Welcome to the presentation with the title Pattern-Based Systems Engineering. My presentation is structured as follows. I will start with a short introduction and will explain the fields of action. The second bullet point represents the main part of the presentation with our results on solution knowledge in systems engineering. The conclusion is an outlook to our future work. Today, complex technical systems, for example in autonomous car or socio-technical production systems, are already based on the close interaction of mechanics, electrics, control engineering, and software. Central challenges in the development of these systems are the increased interdisciplinarity and the increasing complexity of the system to be developed itself. The field of action of model-based systems engineering is illustrated on the right-hand side of this slide. The aim is to achieve a uniform and holistic understanding of the system among all stakeholders involved. Therefore, the system to be developed is described with the help of a system model specified by languages like SysML or Consens. In the context of model-based systems engineering, the reuse of unsuccessfully applied solution knowledge plays an increasingly important role. Therefore, we provide the use of solution patterns. A solution pattern describes a problem as well as the core of the solution for this problem. But what is necessary for a consistent use of solution patterns along a product development? First, we need a uniform documentation of solution knowledge, so a suitable structure is necessary. And second, a systematic approach is required to identify, document, and apply solution patterns for systems design. In the following, I will present our results in the context of pattern-based systems engineering. The results are structured according to the fields of action in 2 points. First, the documentation of solution patterns, and second, a procedure model. According to the most cited definition of the architect Alexander, the solution patterns are divided into 4 categories: name, problem, solution, and context. Relevant solution knowledge is presented by the specification technique Consens. However, this can be replaced by the SysML or similar languages. In the center is a unique name of pattern. The aspect features and functions represent the problem to be solved. Both aspects should be described as solution neutral as possible. The description of the solution consists of the active structure and the behavior. The active structure represents the system elements and their relationship to each other. The behavior models complete the solution description and are represented by activities, state, or sequence diagrams. The aspect context contains applications in which the solution pattern has already been used successfully. Solution patterns can be characterized along different dimensions: type of knowledge representation, specialization of solution knowledge, and aggregation of solution knowledge. The height of the room describes the type of knowledge representation which can be used to record the relationship to discipline-specific solution patterns. Depending on the methods in the individual disciplines, information can be represented differently in the patterns. I distinguish between text-based representation and representation using semi-formal or formal models. With regard to the specialization of the solution knowledge, I can say the more specialized a solution pattern, the less transferable it is. The more generalized a solution pattern is, the more it loses its relation to real problems. The third dimension of the knowledge space illustrates the aggregation of solution knowledge from elementary to complex, so the nesting of solution patterns into each other. This slide presents a systematic for the use of solution patterns in the design of complex technical systems. Like common approaches, also a function-oriented design is taken up. The procedure model describes well-established design steps and it is divided into 5 phases. So it starts with an initial target definition and ends with a holistic system model, which is built up by using well-proved solution knowledge in form of solution patterns. Due to the short time, I would like to refer to the detailed paper, which illustrates the use of the method in the application example of 2 cooperating Delta robots. So let's come to the outlook. In our future work, we will focus on solution patterns in areas such as service engineering or strategic production planning to create a holistic pattern language for systems engineering. Thank you for your attention.
Okay. Thanks for the presentation. I'm not sure, Mr. Anacker, are you in the chat?
I don't see him.
Okay, so it's a little bit difficult about questions. Do anyone has a question to Mr. Anacker? Maybe we can, nevertheless, we can discuss this a little bit. No questions here? Okay. Okay, that's a pity that he is not here, but nevertheless. Let's start with the second paper. The presenter of the second paper, Mr. Müller, is available. I can see him. Hopefully he's available.
I'm here, yes.
Yeah, great. That's really nice.
Maria Siiskonen is actually presenting the presentation.
Okay,
She's also
okay,
here.
Yeah, okay. The topic is about lessons learned from the application of enhanced function means modeling. I have only the CV from you, Mr. Müller. Maybe Maria Siiskonen, you can introduce yourself a little bit, please.
Yeah, so me and Jakob, we're actually both PhD students at the Chalmers University of Technology. And we co-wrote this paper, and also Professor Johan Malmqvist, who is our professor here. And enjoy the presentation, I guess.
Thank you. Irene, would you start?
Hi, this is the presentation of the paper Lessons Learned from the Application of Enhanced Function Means Modeling, co-authored by Jakob Müller, Maria Siiskonen, and Johan Malmqvist from Chalmers University of Technology. The topic addressed in this paper is function modeling, which is an approach to support product design, since it enables the analysis of the justifications for the design and creates a common understanding of a design by exploring the design rationale. And the aim of this paper was to study one specific function modeling method, the enhanced function means method, which has been widely used by the systems engineering design research group at Chalmers. So what we did was we studied projects 20 years back, which has been conducted in collaboration with the industry, basically to see why this method was used, what the benefits of using this method is, and what challenges or limitations we have when using this method. Here I will briefly demonstrate how the enhanced function means modeling approach works, and I will use the example of a glue gun. What you do first is you define the overall functional requirement, which in a glue gun case would be to provide a stream of molten glue from sticks. Then you define the design solution to this, which would be a glue gun. A glue gun then has several other functional requirements. For example, it needs to melt the glue stick, which could be solved by a design solution, a thermal element. Also, we need to be able to control the gun, so we suggest a design solution, pistol grip for that. And for example, we have different parts of the glue gun that needs to be contained in something, and we suggest a casing for that. We can also constrain design solutions. For example, in this case, the thermal element needs to be fitting with the whatever glue stick material we have. And also we can identify interaction between the design solutions. For example, the thermal element needs to fit into the casing that we define. We can also assign alternative design solutions to a functional requirement. For example, instead of a pistol grip, we could have a pen shape, but this means when we generate the concepts in the end, we can have a concept that has a pistol grip or a pen shape, but not both at the same time. Moving on to our findings. EFM has been used, for example, for mass customization approaches, where you can use EFM as a foundation for product platform modeling. Concurrent engineering, you can model life cycle phases of a design and the connections between these. Set-based design, as I described, the generation of alternative concepts, and design space exploration by creating a variety of products within the functioning bandwidth. You can create a design space and explore this. To mention a few of the benefits that we found, for example, the design space is kept open, but then again we can use constraints to filter infeasible design alternatives early on. We can analyze some initial product behavior before we define the geometry of the design, and also we can justify chosen functions and means of the design. But then again, a few of the limitations would be that the feedback from industrial practitioners was that the method is complex and hard to work with, and we need to complement with additional tools to provide for behavior modeling, for example, CAD models. And also, it doesn't give us the geometrical definition, and we need to complement with approaches for this. To conclude, the EFM method has been used for mass customization, concurrent engineering, set-based design, and design space exploration approaches. But then again, the abstract modeling approach has been viewed difficult for industrial application, and we need to complement with other approaches to define the geometrical representation of the design. Thank you.
Thank you for the presentation. Very interesting topic. Are there some questions to Maria or Jakob? So I have a question. You explained that the companies use this. Do they use this in a research project, or do they use this in the daily work in the company? It's more for understanding.
Right now, we only use it in research projects. That's also explained in the paper. There is a big abstraction hurdle that keeps practitioners from really enjoying and appreciating the use of it. We have a good list of well-documented benefits of the approach, but you also don't have a proper software that makes it usable in a practical application. So this is one of the major negative points we have also named in the paper. So sadly, no real application yet, which goes in line with other literature findings. I think Tomiyama wrote a big paper about that.
Yeah, okay. Now we have 2 questions from Mr. James Gopsill. Do you want to ask your questions yourself?
Oh, we can just read them.
Okay, so I can read. How did the design space of the FM compare to that of FM? Oh, now he's here.
Yes,
Now he
just joining in on the chat. So I'm still learning myself around hopping. Yes, thank you very much for your presentation. Hopefully you can hear me. Am I sharing my mic? Good. Yeah, so I just, like you say, it's a building built on functional modeling. So I wanted to know, did your study compare designers using EFM to FM, and how did the design space that they explored? Was it revolutionary different? Did they look at different aspects of the design space through EFM to FM? Yeah, could you just elaborate on a bit more about what were the findings there?
Really good question. Sadly, we haven't directly compared, let's call it traditional function modeling or traditional function means modeling with enhanced function means modeling. We only have first-hand data of function means modeling from student work, and we want to compare practitioner applications. And also, since the paper might have a slight bias from our in-team view, for us, enhanced function means modeling is logical development of function means modeling. So we see it as 2 apples from the same tree, and haven't actually looked into direct comparison. From a design space description point of view, enhanced function means modeling uses constraints as active modeling elements in the representation of the design space, and therefore enables a much clearer definition of the borders of the design space.
Indeed, that's why I think it'd be really interesting to do that extra, additional study comparing to FM.
Definitely. Yes.
By capturing those constraints, does, like you say, embodying them and making them really explicit, does that affect a designer? Because it may be that, leaving it a bit unconstrained gets them to explore different areas compared to when it is clearly defined and constrained. So yeah, exciting work, and yeah, look forward to seeing more of it.
We have a study, I just have to find the title, where we explicitly investigated into very detailed constraint modeling on redesign for AM. I just look into.
That'd be fantastic. Yeah, if you post it into chat, then yeah, I'll gladly read it. That'd be good.
Yep, I'll copy a citation in the chat.
Awesome, fantastic. Thank you very much.
Welcome.
Some more questions. So one question from my side. Normally in the companies, most of the companies working with PLM concepts. In these PLM concepts, they have a product architecture which is structure oriented. And does it fit? Yeah, or how do we have to organize product lifecycle management if we want to use such function oriented approaches to support this creative stage of design?
The short answer is totally differently. Since a lot of the structure is structured due to manufacturing design decisions or other logistical constraints which are not explicitly captured. And so these are not the let's call it modularization or segmentation in the regular PLM systems is not based on the function. So the structures, they don't match very well. I think in PAL bytes, there is the meters diamond where the function structure and the function-based product structure and the geometry-based product structure, they meet at the feature level, but on each sides, they look totally different. So it would require a parallel data management system or a restructuring of the existing one. So no, we don't have a compatibility yet, sadly.
Yeah, and I'm afraid, or we made the experiences. This is the reason why such function-oriented methods, that's not only functional modeling, like you explained, they are difficult to, how to say, to integrate in the processes. Yeah, I think you have same experiences in this way.
That is actually the research topic of my PhD, how to couple this function modeling stuff to the geometry. I don't go all the way into the PLM, but we have developed now in our research team a prototype or a proof of concept of a method that at least goes CAD model to function model. And we see the same modularization structure on both ends. And the initial tests with industry have been relatively positive, but it's very young, the research. And probably in 2 to 5 years, we can say if it's feasible.
Okay, good luck for this. Thank you for the presentation, for the discussion. We have a very strong schedule, so we have to start with the next presenter. The next presenter will be James. Yeah, his topic is covert graphs for design and manufacture knowledge mapping. James is a lecturer in engineering design at the University of Bath and researcher in residence at the National Composite Center in Bristol. He's interested in democratizing design, prototyping, knowledge management, and complex systems. Please, it's yours. Yeah.
Awesome. Do I need to do anything now? Okay, it's going. Okay. My name is Dr. James Gopsill, and I'm a research fellow for the Centre for Modelling and Simulation and University of Bristol. Knowledge mapping remains a critical activity in engineering organisations, with current techniques for effective mapping employing interviews, consultations, and appraisals. One example is a timber construction company that used interviews and surveys with employees on 60 timber structure projects over a 6-month period. So knowledge mapping is a huge endeavour and activity for organisations to undertake. Technical reporting remains one of the main forms of knowledge capture, and the advent of digital document management systems has provided an accessible store that could be used to automatically analyse the knowledge within an organization using data mining algorithms. So our research question was, can coword analysis be applied to full body text to identify keywords and topics for an organization's knowledge map? Coword analysis is the investigation of the semantic structure of a corpus of textual data through the co-occurrence of terms. We primarily see coword analysis being used on scientific literature, so be it journal series or conference series, where researchers have pulled out the keywords from the front pages of each of those conferences and journals and look to identify the co-occurrence of those terms between the documents. So a co-occurrence of a keyword on a document would then form a link in the network. That network link would increase in weight and importance if more documents had those two words within it. So what we then create is a coword network, as you can see on figure 1, which enables then clustering, critical path analysis, and advanced visualization techniques just to be able to understand the knowledge topics that were being discussed in a particular conference or journal series. So we were looking to do that with, technical reports in a engineering company and organization. We were working with the National Composite Center and we used a series of technical reports from their R&D corpus. So the National Composites Centre is a world-leading research and development centre for composites, UK composites research, performing lots of projects with industry and academia, precisely in the low TRL levels. So their knowledge discovery is incredibly quick and at a very high rate. So they're looking for new techniques that they can then create knowledge maps that evolve and update on a monthly basis. So the document set today can be detailed in table 1, and we're just taking a subset and seeing if we can apply code analysis to the entire data corpus there. So looking at the paragraphs of text as well as the keywords within those. So trying to get an idea of the emerging keywords within the corpus as well as the ones that have been already identified by experts. So what we did then is create that keyword network through the document set, and we were then looking to see if the graph properties can actually elicit keywords. So we had a series of experts identify a set of keywords within those technical documents as well as a set of non-keywords. We then looked at the properties of those keywords within the graph and looked at their document frequency, degree, weighted degree, eigenvector centralities. And what we found out is actually the graph properties were statistically significant in identifying or being able to distinguish between a word or a bigram that was key or non-key to an expert, or what they would consider useful for identifying topics and knowledge within the corpus. We then took the subset of keywords, identifying those within that network, and looked to see how clustering techniques could be used to identify topics within the corpus. So we also compared those with a set of clustering performed by experts at the NCC. So taking the same keywords and manually clustering them to a clustering technique automatically applied to the network. What we found was that even though the network clustered very well using the automated, algorithmic methods, that the actual clusters, if you compared them to the clustering that the experts performed, they did not correlate that well. They were actually identifying different types of topic within that. One suggestion is actually, because we're analysing the entire technical report, it may be that the linking between the keywords within those reports is more procedural than what you might think as more of a knowledge map or knowledge topic. So more work is required there to understand what kind of topics it's actually generating from those clustering activities. So just to conclude, t-tests were showing that graph properties can be used to distinguish bigrams or keywords within those networks. Partitioning did perform well in identifying topics, but those topics were not typical of what an expert would perceive as a topic, a knowledge topic. So more work needs to be done to understand what the difference is between those clustering methods. So the DMF lab, we are keen to collaborate on any knowledge management data science activities. We have been doing this for a number of years now, so keen to share our knowledge and share our algorithms with people. So please check us out at dmflab.co.uk. So thank you for your attention, and I look forward to hearing your questions.
Thank you very much for the presentation. Sorry, are there some questions?
Yeah, sorry, my green screen, I haven't got it working yet. That's it. I don't know how to turn it on in Hopin yet. That's it.
So at the moment, I don't see a question. I have a short one. You spoke about knowledge, but my feeling is knowledge has a kind of dynamic component, because what I think what you have shown is more information, because knowledge is connected with the process, with this learning process. How can you be sure that you have really knowledge, not information? How can you identify or figure out this learning process behind?
Indeed,
knowledge?
That is one of the key challenges, actually. Like I say, yes, technically you'd probably call them, like say, information topics, most likely, because like say that knowledge element, you're entirely right, there is that learning element of transferring it between individuals and communities. One of the things with the National Composites Centre want to really achieve with this is one of their big, like say, success is that they train up individuals in composites research, and then they go out into industry because they get effectively pinched by industry because they've got this deep domain knowledge. So part of this activity was to, you know, capture the, let's say, yeah, you could say the information topics that are of interest. And before those individuals do leave or transfer, is to ensure that they introduce new activities within the NCC. So they are providing communities of practice. So they identify a topic, they can identify the leaders in that topic because we know the authors of those documents. And then actually, like you say, is probably that next step, which is actually the knowledge transfer between individuals, where actually using this as just a means of saying, well, what communities of practice should we be generating, and encouraging people to communicate and share their knowledge so that they can keep it within the organization. Because that's one of the gaps they found, is that when an individual leaves or a couple of individuals leaves, then they suddenly lose that knowledge of a manufacturing process or a novel new idea. So yeah, I totally agree with you in that respect. So that's where it's going.
Thank you. We have a question in the chat. David, would you ask your question yourself? Otherwise,
that's okay. Yeah, I can see it. Yeah, so I'm happy to go. So yeah, so David's just asked, is there any way to use the domain expert clustering to improve the automated process? Indeed, yes. Again, that's one area that we might explore, and that is the next steps, is to see if there's any way we could maybe potentially apply some kind of machine learning to see if we can assist the clustering technique and make it more representative of an expert. So effectively customize the clustering technique in that during that process. So definitely we might look like at a mixed methods approach. One aspect is supervised learning that we're looking at. So that's it. You could nominate a keyword or topic to an expert, and they can be more of a Boolean yes or no, we agree. And if they agree, of course, it gets appended to a topic map, or appended to their knowledge map. And if not, it is left out. We then have a data set of true and false that we can then use to optimize and improve the actual automated algorithm. So yeah, that's it, definitely.
Okay, thank you. Is this the answer you want to have, David?
I'm sure he does. That's it. I know him. Yes, I know him quite well. So yeah.
Okay, so it's not a problem if you don't have a camera. Your die Stimme is enough. Your voice is enough. Okay, are there some more questions to James?
I have one question. So
Yes,
if I understood you correctly, you are able to find some keywords and some knowledge topics in these reports, for example. Are you also able to see, well, how important is this keyword, for example, in this technical reports or report, so that you can also see if in the context of this whole report, this keyword is also something that you really need, or if it's just an example, for example?
Definitely, yes. I mean, I'll probably try and post in the chat another paper that we were working on in this. One area that we're looking at, because of course, you know, these documents are being generated on a monthly or weekly basis. So we are actually producing dynamic networks. So yeah, and you can weight them primarily on how often those keywords are used within those documents. And we are using that to trend through time what is the what are the emerging topics and which ones are the declining topics. And you can, of course, see patterns in the projects that they're receiving with companies and organizations of where what's the primary expertise they need at any one point in time. And we're starting to use it for strategy. So for R&D projects going forward, when we're bidding for innovate funding or grant funding, we can identify and have actually some kind of rationale for why we're identifying an area to develop further, because we can see it growing in the network as this topic that's been growing, because there's more and more reports being done in that space. And we can go, to be able to take that to the next level in, like, say, the technology readiness levels, and to get it to a technology that industry can use, we need to do this X amount of research, you know. So we're using it as a way of providing that quantitative, you know, evidence-based argument for grant funding.
Okay, thanks.
Okay, if there are no more questions, thank you again for the presentation and also for the nice answers. Thank you. So the next,
No problems at all.
sorry?
You're welcome.
Okay. Okay, the next presenter is Siniša Kolarić, and she will present the result of a cooperation between the Georgia Institute of Technology, Milwaukee School of Engineering, and Indiana University. The topic is on the hierarchical levels of design knowledge. Please, can we start the presentation?
Hello, my name is Siniša Kolarić, and this is our brief presentation on the hierarchical levels of design knowledge. To begin with, there are of course many perspectives on design. One perspective, and which we adopt for this work, is the knowledge-centric or epistemological perspective. In other words, design can also be viewed as a process that generates various bodies of design knowledge, or BDKs. Within this perspective, open questions may include: what are the ends or purposes, that is, teleology of design relative to this perspective? Next, what are some of the typical bodies of design knowledge? And finally, can we organize BDKs into a unifying structure or map? Our motivation for this work stems from an interaction design project titled Cambria, during which we identified a number of BDKs. We list these BDKs in the fourth column of this table, divided by the stage during which they were initiated. At the end of the project, we ask ourselves, is there a way to arrange all these BDKs into an organizing structure? By reflecting on design research and development outcomes, we realize that we can organize BDKs into a hierarchy, which we name the CDH model of design knowledge, and which consists of three principal levels: contextual design knowledge, design development knowledge, and high-level design knowledge. Contextual design knowledge consists of detected contextual entities, triaged contextual entities, and the design brief. Building upon the contextual design knowledge, we have knowledge about design states, which we call design development knowledge. Following the common three-way classification of design states, we have conceptual design states, intermediate design states, and final design states that can be used for realizing the final product. Based on the experience accumulated by developing many design states, possibly over multiple design projects within the same design sub-discipline, a designer or design researcher may optionally proceed with the generation of high-level design knowledge. In the current iteration of the CDH model, high-level design knowledge consists of design patterns, design guidelines, design principles, design laws, and design theories. As for related work, we give a more complete list of past approaches in our paper, but to illustrate, Nelson and Stolterman proposed this simple model of design, which consists of not knowing, knowing, understanding, and wisdom, which closely reflects the CDH model. As another representative example of related work, a number of hierarchical models of knowledge have been proposed in non-design fields of inquiry, such as this DIKW model in the field of information management, which consists of data, information, knowledge, and wisdom levels. Among the benefits of our CDH model, we argue that it affords a cognitive model or a cognitive map that is invariant across various design disciplines with regards to design knowledge. Then, it may also be used to explain the genesis of previously synthesized design knowledge. And finally, the CDH model may also be used as a roadmap to develop a desired body of design knowledge. For example, a set of design guidelines for a specific class of design problems. As a summary, in this paper we have introduced a three-level CDH hierarchical model of design knowledge. We argue that this model can help with mapping BDKs created in design practice and design-based research, as well as inform future research related to the epistemological foundations of design practice and design-based research. Future work includes augmenting the CDH model with additional BDKs as they are discovered, suggested, or proposed by design researchers, then listing and describing methods for generating and validating BDKs, clarifying the temporal aspects of the model, for example, how are individual BDKs refined in time, and finally, further exploration of the nature of links and feedback loops among individual BDKs. This concludes our presentation. If you have any questions or would like to collaborate on this research, please do get in touch, and thank you for your attention.
Okay, thank you. Is there someone of the authors in the chat? Nobody here. That makes it difficult to have questions to him. Are there some questions to this presentation?
Hi, Kristin. I would have said, you know, I would have liked to see a practical example of one compared to another, but as they're not here, I can't really ask if ask them. But I'm sure I'll follow up with them.
Okay. Okay, so then let's start with the last presentation in this session. The last presentation is prepared by Philipp Wolniak. He is from the Leibniz University in Hanover in Germany, and I think he's a PhD student there, and his topic is automated product functionality and design optimization, instancing a product service system.
Thank you
Please,
for the
Philipp, it's
introduction.
yours.
Welcome to the presentation of the paper with the title Automated Product Functionality and Design Optimization Instancing a Product Service System. To start, the motivation for the whole topic. What we are looking at is some kind of a standard product development for a mass market, for example. At the beginning of such a development, we have the requirement specification according to a market analysis, for example, that we did before. So we are trying to get the requirements for most of our customers, and we get some kind of a one-fits-all product. What we also see is that a strict requirement specification often restricts the development freedoms, and that we then do not fit all the requirements for all of our customers. So what would be best would be a customization to the customer-specific needs. We then have a higher degree of freedom to adapt our product to the needs of the customer, and a value-adjusted production. So when, for example, a customer needs a lower size product or with less power, we can adapt our production to this. What this also imposes is a necessary dynamic and flexible reaction to market situation or customer changes. So we then have some kind of user scenarios. We have a high spectrum of possible solutions to this that we have to assess. With that, we also have a high number of then often cumbersome manual analysis synthesis routines. So let's say we have some kind of a CAD model, we have a simulation model, we have to change parameters, we have to do this manually, and this takes time and resource consuming. So the idea is to use some kind of a design automation to overcome this problem. With design automation, also what is necessary is a robust model or several robust models, and this is what this topic is all about. In our approach, we focus on functional products, although we could also use this for example, structural components. The design automation is performed using an optimization algorithm. So we see the optimization algorithm as the leading instance. So we have some kind of a script for starting, refreshing every model and so on, and this optimization algorithm performs this evaluation. The challenge in this approach is the formalization of the impact of changes in our models. So when we change some kind of parameter to meet the requirements, we have to be able to assess exactly what is the actual outcome in the functional model or in geometric model and so on. And therefore our approach is to use two separate models. So we have one function analysis model where we can analyze our product and see what is the objective, what is the actual value of our objective function. And we have a geometric model where we can assess if a change of a parameter in the real instance leads to a feasible solution. So the optimization algorithm sets the parameter values in the function analysis model. It starts the simulation, it evaluates the simulation, and we get the property values back to the optimization algorithm to use them in our objective function. In the second step, the optimization algorithm sets the parameter values in the geometric model. The geometric model builds itself up and it transfers the feasibility to the optimization algorithm to also assess the outcome on the objective function. For our use case study, we performed a use case specific optimization of a coffee machine. For this, we used an exemplary distribution of customers in a hotel in the period of 3 hours in the morning, which you can see in the diagram above. On the right-hand side, you can see a simplified geometric model of the coffee machine with some significant components for the timely serving effectiveness of this machine, like a brewing unit, a buffer tank for storing already brewed coffee, and so on. Several of these components have parameters specified as input variables for the following optimization, and which therefore affect the objective function of an effective coffee serving. In combination with the functional model of the serving process, you can see the optimization process with an isometric overview and a close-up of the brewing chamber on the left-hand side and the optimization convergence on the right-hand side. In this convergence diagram, you can see in the upper part the distribution of the parameters like the brewing chamber diameter, height, or even a discretely changed parameter like the power class of the water pumps. In the lower diagrams, you can see the distribution of the objective function throughout the optimization, where every blue dot represents a valid solution of the parameter combination, while a red cross marks a restriction violation. A violation may be, for example, that any component in the isometric overview intersects with a transparent envelope which displays the overall restriction of the size of the coffee machine. At the end, you can see that the optimization routine converged to a suitable solution regarding the functional effectiveness and the geometric feasibility. And with that, I end my presentation and I thank you for your attention.
Okay, thank you for the presentation. Are there some questions to Philipp?
May I go? Yeah. Is that, yes. Hi, Philipp. Thank you very much for your presentation.
Yeah, please.
Really insightful, like you say. We do a lot of stuff on what we term as digital twin. Probably in, the buzzword of the day for these kind of technologies. So really interesting to see, your approach to it. One aspect I was going to ask about is the nature of the parameters that you're exploring. Are they all continuous variables, or do you have some discontinuous parameters? Let's say a block can be here, but not in the middle. And how does your optimization algorithm deal with those kind of jumps between design spaces that may be not fully connected?
Yeah, thank you for your question. We also have discontinuous parameters. So what I tried to show in the last page is that we have, for example, the discontinuity of the pumps that we use. We had 3 classes of pumps, and if the optimization algorithm shows one value between the threshold of 0 to 0.33, for example, then we used one kind of pump. And then the representation in the functional model and in the geometric model changed to this representation in this value. And there is, of course, a problem in the objective function space. So we have jumps in this space. But what we have seen is that this optimization algorithm, over time, if you use enough evaluation, then it converges to one kind of pump class in this case. And then we have found a solution. But of course, if we use more and more of these discontinuous parameters, then it will get more and more difficult. Yeah.
Oh, fantastic. Thank you. And just, if I may, just to follow on that, if, on a technical standpoint, in terms of how much of the design space do you actually cover in terms of generating solutions? Do you, technically, you probably could work out that this solution space is of X size. How does your optimization algorithm navigate it? Does it cover about 20% of the space or 10%? Is it quite efficient in covering the space? Could you allude to some of that on your optimization algorithm?
Yeah, in this case study that we used, we only looked at one concept of this machine. So we have one concept, we have one position for every component that we have seen right there. And then we exchange parameters, and then those components adapt to this. What we are looking at right now is to broaden this up and to give the possibility to also look at other concepts. So, for example, that not only this kind of component can be used in there, but also other kinds, so that these design elements, we call them, are also automatically exchanged by the optimization algorithm. And therefore, we can also look at other concepts, which of course would broaden the solution space. So right now, with this case study that we used, it is a rather low solution space, but we are looking at broadening this up and have a more automation of the whole concept finding in the of the concept finding.
Fantastic, thank you very much.
Yeah, thanks.
Yeah, there is another question by Johan. May I read? Philipp, since your paper mentions the calculation time is mostly controlled by limiting the amount of iterations, did you look into sensitive analysis to identify the most influencing parameters and thereby reduce the amount of parameters to optimize?
Very good question, a very good remark. That's something that we are doing, or we already have done. That's also, of course, typical that for something that you do in optimization. So we had now 5 optimization parameters. Of course, there are in the actual development, there are more parameters, and then it is feasible and very good to use some kind of sensitivity analysis, and that's what we are doing right now. Yeah.
Okay. One question from my side. My feeling is there are some similarities to use or to additive manufacturing. There we use topology optimization to create parts. And it seems you have used this principal approach not only to design parts, but also to design overall systems or components or more than one part. The problem we get then, the idea seems to be great, so I like it. The problem may be that in this situation, we not only have mechanical problems, we also have to consider electronical physics and informatics and so on, and maybe there is another kind of mathematics behind. Do you have think about these effects, or do you deal with questions in this direction?
So what we're looking right now is that we also have the function of the whole product that we are looking at. So we had a functional model, which, for example, calculated how much time does it need to serve 1 cup of coffee, and how much time does it need to serve all cups of coffee when there are coming 20 persons, for example. And so we optimized this product according to the persons that were coming, and to have a optimized product for this. Of course, there's not only the part of this functional, but as you said, there are also some electrical domains and so on. So this is something that would be, let's say, a third model that would have to be coupled with the others. And so we are looking at it that every domain that we want to optimize needs a singular model. And so then all of these models have to be coupled together.
Okay, thank you. Okay, are there some more questions? Oh, okay. So we are good in time. We have 5 minutes left over. Thank you for all the presentations. Thanks to the presenters to prepare these presentations. It's a pity that we can't meet directly, but I think such a virtual meeting is better than nothing. Hope you enjoyed this a little bit. If you have some hints, or if you have some ideas how to better organize such conferences or such sessions, please write it in the chat. We will be very thankful if we get some hints how to make it better, or how to support such conferences. Yeah, hope you had enjoyed this session, and so hope you will enjoy the next sessions too. Thank you all for presenting and for taking part in this session.